I now want to consider what is known as the SAS inequality. Let's suppose we have two triangles that have a pair of corresponding sides congruent. So I'm going to go ahead and draw these two triangles down here. Here's one and the other. Not perfectly drawn to scale, but that's okay. I know that they both have these corresponding sides are congruent. However, if I look at the included angles, this one, which I'll call 1, and this one, which I'll call 2, we know that one of them is larger. So let's say angle 1 is larger than angle 2. Then this side, A, needs to be bigger than B. In my last video, I talked about how a larger angle means a longer side, and a longer side means a larger angle. However, that was if we were considering a single triangle, and the SAS inequality is what is allowing us to expand that in general. If I know that I have two congruent sides, and one angle is bigger, then I can say the third side is also going to be bigger. So it expands this idea into looking at comparing two triangles. So let's try to prove this. Here I have these two triangles. I know side AB and side XY are congruent, and side AC and side XZ are congruent. However, I'm going to suppose that angle A is bigger than angle X. I then want to construct this ray AD that comes down here. We'll say D is approximately there, between AB and AC, such that this angle BAD and angle X are congruent. In addition, AD is congruent to XZ. That's why I drew this slightly longer, because it might be longer, it might be a little shorter, but the main thing is this side right here, AD, should be congruent to XZ. We then have that by SAS, if I go ahead and draw this side out, this triangle ABD would be congruent to XYZ, since I have two sides that are equal and an angle. That tells me that this distance BD needs to be equivalent to YZ, since these are congruent triangles. I'm then going to bisect this angle DAC here with this ray AE, where E is on the segment BC. I then know that since AD has to be equal to XZ, which is also equal to AC, by side angle side, this triangle ADE, since we have this side, this angle up here, and the side AE, is congruent to ACE, because once again we have the sides are equivalent, this EA is equivalent to EA, and the angles are equivalent since this was a bisector. This means DE, the third side of this triangle, needs to be equivalent to EC, the third side of this triangle. We can then start looking at the triangle inequality. BC is equal to the distance from B to E plus the distance from E to C, since these are all on a straight line. Well, EC is the same as the distance from E to D by these congruent triangles here. And that needs to be greater than the distance from B to D by the triangle inequality. But we also know the distance from B to D is equal to the distance from Y to Z, once again by congruent triangles. So now I have that BC is greater than YZ, which is exactly what we needed. The third side of this triangle has to be bigger than the third side of this one, since we're looking at the fact that angle A was larger than angle X. I now want to prove the other direction. Let's suppose segment BC is bigger than segment YZ. Then we need to be able to show that angle A is bigger than angle X. Then one of three things must be true. Angle A is greater than angle X, they're equal, or angle A is smaller. If angle A is smaller, then by what we just proved, side BC would need to be smaller than side YZ, since we showed that smaller angles will result in smaller sides. And that gives me a contradiction. If angle A and angle X are equal, then I have two sides of these triangles congruent, and the included angle is congruent. So by side angle side, these triangles would be congruent, meaning that side BC is equal to side YZ. Also a contradiction. So we must have that angle A is the larger of the two.